more people to log in. And I'd like to welcome everybody to the second talk in the CIG Webinar series. Just as a reminder, the overall aim of the CIG Webinar series is to connect mathematicians to computer scientists to geoscientists, among others. Presentations in the series will be approximately 45 minutes in length, with questions and answers following during the remaining time. These webinars are being recorded and will be available for on-demand viewing through geodynamics.org and through YouTube. During the seminar, only the host and presenter will have their microphones enabled, so use the chat window to type in your questions or to communicate with others. There's also a slight audio delay and video delay, so please be patient while the screens are changing. As a heads up for the next webinar, there will be none in December due to AGU. Our next webinar will be in January by Jed Brown, titled High Performance Implicit Solvers for Geodynamics, and that will be on January 10th at 2 p.m. So for today we have Timo Heister. Timo is a visiting professor in the Department of Mathematics at Texas A&M and also currently a postdoctoral fellow with the Institute for Applied Mathematics and Computational Science through KAUST. Timo received his Ph.D. from the University of Göttingen, studying a massively parallel finite element framework with application to incompressible flows. His research interests in incompressible flows include many mathematical and computational methods applicable to Mantle convection simulation. Timo is part of the team implementing the new aspect Mantle convection code that uses these modern numerical methods and builds on a set of existing high-quality software libraries. Today he will be talking about this work and show us real-time examples in his webinar, Modern Numerical Methods for Modeling Convection in the Earth's Mantle. So if you all be patient just for a moment, we will transfer control to Timo and he will start his seminar.
Okay, can you guys hear me? Okay, I'm not sure if my screen is shared right now. I think that's not the case yet. Share my desktop. Okay, that looks better. Final check. Does that work now? Okay. Welcome everybody, and sorry that my internet kicked me out right at the moment when Lorraine introduced me. This is my first webinar, so please interrupt me or let me know if there's a problem. And if I hear nothing in the comments, I will get started. Better on page 1. Okay, so I'm going to talk about the finite element code aspect and a bit about the background around this. This is joint work together with Wolfgang Bangerth, and he and I together are the main authors of the package aspect. Before I start, I will try to look into the comments again. Okay, nothing in there. Good. So let's get started. I will mainly talk about the code aspect after a short introduction, what it is and why you should care. I will do a short hands-on session, and I hope that it's going to work out. So I'm going to run aspect live, and I'll show you a few tricks and so on and so on. And then I go back to slides and give you guys some background, some more examples, some more fancy stuff, yeah, and I hope this gives a good introduction to aspect and what we are doing. So, what is aspect? Well, it's an acronym, or a bad acronym, for Advanced Solver for Problems in Earth's Convection. It's an open source C++ code. You can get it at dl2.org/aspect. And it's based on the finite element library dl2. Well, it's also hosted under the domain of dl2. And in the last webinar, Wolfgang talked about dl2, the finite element library. So I'm not going to do that now, but we're using it, unsurprisingly. So this is a project that is supported by CIG, what we are grateful for. And it's a pretty young project. So our first release was earlier this year. There's been a lot of change since the last release. You can find more about this at our website and about dl2 online too. Okay, so what are our aims? The first thing is we want it to be very easy to use and to be extensible. We are mathematicians, so we are coming from the point of understanding the numerical methods, and so we want to bring modern numerical methods to the geoscience community. One thing that we think is important is to have a parallel code that has very good scalability. If you think about the future, the problems are really going to be really big, and so you need a code that supports that. We don't want to reinvent the wheel, so we're building on others' work. There are thousands of man-hours of work in DL2, and so we are using this library. And I would also like to point out that this is we are very inclusive, and we see that this can only succeed as a community. So we hope that you guys are interested in working with us. And at this time, I would like to take the time to shout out to thanks to many of the many contributors that we already have: Markus Birk, Juliane Dannberg, René Gassmöller, Thomas Gehn, Erik Hein, Martin Kronbichter, and probably a couple of others that I forgot. Okay. So nothing there yet. So what is the goal? Well, we want to simulate the convection of the Earth's mantle. So if you look at this picture, we have the core, we have the crust that is solid that we live on, and in between we have the mantle. It is mostly solid material, and it has very slow velocities, and is driven by temperature differences. So material gets heated up close to the core because the core is hot, and so the hot material rises up and cools in the process and then goes down again. Okay. Why is this of interest? Well, there are many questions that you can ask. What exactly is inside the Earth? We cannot really drill down deep enough to see what's going on. It's still a question what exactly drives the motion of the plates. We don't have the full thermal history of our Earth, and we don't really know how long did mantle convection exist, and does it exist on other planets or not. And all these questions you can try to answer if you do simulations, because then you can match it with your measurements of today and then see which models work and try to answer these questions. Let me motivate why we need high-performance computing. So this is a snapshot of a 2D computation done with Aspect. This has 700,000 unknowns, which is a small amount. The graphic here is symmetric. On the left, you just see the temperature, and on the right, you see the computational mesh. And you see that there are very small features, these plumes rising, and you need to capture those. And you can only do this with adaptive mesh refinement. Otherwise, especially in 3D, it's way too big. To give those some numbers, the mantle is about 3,000 kilometers deep, and a plume can be smaller than 10 kilometers. And if you think you want to simulate the whole Earth in 3D, you cannot do this with a isotropic mesh. So you need adaptive mesh refinement. But even still, you have 100 million or more unknowns for a very realistic computation. So you need access to large computers and high-performance computing, and you need to write the software to be able to do this. I guess that's pretty obvious from these size of systems, because if you have 100 million unknowns, that means that you have a linear system to solve that is 100 million times 100 million big. Yes, that is very large. Okay, so what are the equations that we need to solve? Well, we kind of need to solve for a velocity, a pressure, and a temperature. And these equations here describe, the first two describe the flow of the velocity and the pressure. And the third equation is convection diffusion equation for the temperature. And what happens is that, well, the velocity advects the temperature around, and the temperature diffuses a little bit. And on the other hand, the temperature causes a density difference and thus drives the flow. Hot material rises. Okay. There are a lot of things on the right-hand side, like radioactive decay, friction heating, adiabatic compression, and so on, that I didn't want to write here on the slide. You can look into the manual of Aspect and where it is explained. You might also have additional compositional fields that you want to track around to have different materials. Note that the density here is not an unknown, but it is a function of, for example, pressure and temperature. So we're not running a fully compressible model. Let me check if there's anything going on. Nope. Okay. So what are the challenges? The problem is that these equations look okay to model and simulate, but the problem is that we have very complicated material models. All the coefficients, like the viscosity and the density, they depend non-linearly on everything else: pressure, temperature, strain rate, chemical composition, if you have that, and so on and so on. And there are different challenges. For example, the viscosity changes many orders of magnitude. The compressibility is hard to solve, and so on. So you cannot envision solving all of these things exactly. We also have the problem that we don't really know how these material models work, for example. So you kind of have to make some compromises. You have to make simplifications. The question is where? What is the right model to use? I don't know it, and I'm probably right in saying that you guys also don't know that. So what is the answer to that is we need to be flexible. So we need to be able to try out different material models. We need to compare them. And we need to, well, our code needs to be able to do that, okay? And I'd like to list some of the features of Aspect. So one of the main things is that I think is really important for software is that it has good documentation. So we right now have a manual that you can look at on the website that has over 100 pages. We have code documentation for all the functionality inside the library if you need to look in there. I don't know how many pages that is. We have examples, or what we call cookbooks, inside the manual where we describe how to set up some of these things. And if you want to learn more about the details, there's also a paper that got accepted that you can read, which is the first paper about Aspect, basically, and explains a lot of the things that I'm touching on today. I also think that it's quite easy to use, even though it's a C++ library. So you can start your simulations by just editing a text file, and you don't need to get into the code. And if you have to get into the code, that's also, you can start very easy writing your own material model, for example. It just takes a couple of lines of code. As I already said, we need to be flexible, and I think we are. Also, about efficiency and parallel scalability, I will talk later on. I will also highlight a few modern numerical methods that we're using. And I will also try to show you that there are many statistics that we are outputting. We have support for many different graphical output formats. You can use many different tools to visualize your results and so on. And what we are working on right now, with the help of some others, is compositional fields. You can do this through fields or through tracers. This is still a bit experimental, but there's some good progress there. So that's about the features. And now I will do a little demo, demonstration of Aspect. So I have to say I have to do this on a Windows machine, so I cannot use my normal machine. And Aspect runs under Linux, so I have to run it Aspect inside a virtual machine, which is somewhat slow. And also, because of that, I can only show simple problems. It is based on, if you want to try it out, if you have Aspect, it's based on the example that's called Convection box. And there's also some more description in the manual for that. Okay, so there are no comments so far. So I will go into the virtual machine, and I hope you guys can see that. And what I'm going to do is I'm going to open up a terminal and go into the Aspect directory. And let me remove everything that is inside the output directory first. Okay, so I'm going to show you one of these parameter files that I use to control Aspect. And this is in Cook's books, and it's basically a copy of Convection box, but I called it test here for the purpose of this discussion. Okay, and so this is a text file. I call it a parameter file. And there are a lot of different sections. There are comments here explaining what everything is. And this is a setup for a benchmark. It's called, it's from a paper from Blankenbach et al. And it's a simple 2D box, constant viscosity, radius 10 to the 4. Oh,
it's good.
oh, thanks, Lorraine. Can you mute yourself again so that the echo goes away? Okay, thank you. So this is the text file. I'm not going to go into all the functionality, but to point it out. So you have some, for example, some initial perturbation that is straight from the paper, the formula for the initial condition. And for example, at the bottom is heated, and I will just run the example so that you see how that works. So I will run with 2 processors because the virtual machine doesn't have more processors. And this is the name of the executable aspect. And now I'm just going to point it at this parameter file, which is called test. And I'm going to run this. And it will produce output in this directory, which is called output in this case. And so on the left, you can see that it is running right now and it's doing its time steps. So let me, while it's doing that, start visit, which is also included in this virtual machine, and just look at a solution. So I'm going into the aspect output directory. These files were not there a minute ago because I deleted them. And what I can do now is, for example, look at the temperature. Okay. This is the temperature field. This is the initial condition, basically. And I can also show you, I can also show you the mesh draw, and I could also look at other variables, but I won't do that for now. So this is the mesh. It's very coarse, as you can see, so that it can run. And so it's still running, but it's got quite far already. So I can not only look at those solutions, and I can also go to the next time step, and you can see that it now does this convection box, so it's heated at the bottom, as you can see. And what I'm now going to show you is a file that is called statistics in the output directory. And this file is written continuously while the program is running, and it's basically one row of numbers that is output for every time step that aspect does. And what is happening here is that we have a lot of statistics. For example, we have which time step are we, what is the time that we are currently at, how many cells do we have, and so on and so on. And for this benchmark, it turns out that we're interested in the heat flux that goes through the different boundaries. So, for example, the 18th column, which is this one here, is the heat flux that goes through at this certain point in time. And, well, that's nice to see. The problem is that I cannot really see what is going on. So what I'm going to do now is I'm going to open GNUplot, which is a simple tool to plot stuff. So what I'm going to do is I'm going to plot output statistics using, so I want, as on my x-axis, I want the time in seconds, and on my y-axis, I want the outward heat flux through boundary 3, which is the top boundary, which is number 18, and I say with lines. Okay, and this is what it's produced. You see that while I was talking, the computation is finished. So it took a minute or 2 to do this computation. And you might ask, well, you see that it converges against a constant solution. You might ask, well, what is that right or not? Well, luckily, the benchmark has a reference value for this. And I will plot this. It's a green line here. I'm not sure it's visible very clearly. I can try to make that a bit bigger. Okay, you can see that, well, we seem to converge to something that is very close, but if we zoom in a little bit further, you can see that we are a couple of % off. Now there are several things we can do. One thing would be that we go in here and search for initial global refinements. So this determines how big the mesh is in the first. We keep it constant, the mesh. The mesh is not changing here. So I could refine it. I could do, for example, 6 here. That would mean we refine the cells twice. We have 16 times as many cells, and we also need to make, I don't know, 5 to 10 times as many time steps. And so this would not take 2 minutes anymore, but it would take half an hour, and I was not going to do that. And instead, what I'm going to Okay, I Hope that I'm back. I'm sorry that I get kicked out for some reason. I'm not sure what's going on here. Yes. Okay. Sorry about that. Let me switch back into the virtual machine. So what I did was I ran this computation beforehand, and I actually didn't run the computation with 6 here, but it's a different one, so I will explain what I did here is. What I did was some trick, namely, I can figure out how to make this bigger. Okay. What I did was that instead of running the whole computation with Refinement 6, what I did was I said, okay, I start with a very coarse mesh at refinement level 3, and then I'm going to do refinements at 0.1, 0.15, and 0.2. And this is the blue line that is plotted here, so it runs a coarse computation that's very fast. And then there's a little bump here when it refines at 0.1 to a finer mesh, and then uses the solution on an even finer mesh and an even finer mesh. And instead of taking an hour to do this computation, it only takes around 10 minutes. I'm not going to let you wait, so this is the solution of that. Sadly, it doesn't continue all the way to the end, but you can see that this converges to a solution that is much closer to what we were trying to have. Okay, seems to be still running. And now I'm going to go back to my test program and let me output into output new. And what I'm going to do now is an even more efficient way to get better refinement. So instead of using 6, I'm using 4 again, which was the one that we used in the very beginning that just took a minute to complete. And now I'm going to increase the polynomial degree of the temperature by 1. I'm going to save this file. I'm going to go back to aspect, and I'm going to run this computation. And now it will crash and will complain that this directory doesn't exist yet because I didn't create it yet. So now I created the directory. I'm going to run it again, the modified file. And now it's going to do its job. I'm doing no additional refinements. And so what we can see in a second, so I have these, and now I need to put in the additional run that I'm doing right now, which was called output new. So let's look at this. I'm zooming out again. So you now see the red computation was the coarse mesh that I did live. The blue computation was the one that I did offline that refined a couple of times and takes a few minutes. And the pink one here is the computation that is running right now. But I can already look at the solution. That's really nice. So I can move this window to the side a bit, and I just have to rerun this plot command, and you can see that the pink line continues slowly. And while that's doing it, I can also comment a few other options that you can use. For example, I already explained roughly how this works with the additional refinement times, which is, by the way, also explained in the manual. What I can also do is, which is here at the top, I can resume a computation. What I can do is I can run, for example, to 0.3, then I can end the run, and I can say every 100 time steps, save out your current state. Then I can do resume equal to true, and I can change parameters. For example, I can then go and say, oh, on second thought, I want to do some refinements. So I can put an additional refinement time at 0.31, for example, and then continue the run where I left off. Let me look how far the computation now is. Where's the GNU plot window? So you can see the magenta line is already halfway through with the computation. So let me zoom in there a bit. We see the red one, which was our first solution. The green one is the reference value that we have. The blue one, well, it didn't complete, but it's somewhere in between here. And you're going to see that the pink one is also pretty good, especially for the fact that it runs live here and is done in a few more seconds. Okay, you can try all this out by yourself, and especially if you're not running it in a virtual machine, it will run much quicker. If there are no questions about this, I will continue with my talk now. So let me check if there's anything. No, nothing so far. Okay, so I'll let this run, and you're welcome to experiment with this. A few things to try out would be, for example, to increase the Rayleigh number to something that the solution is instationary, and then look at the solution, and so on and so on. Okay, so I will cancel that, and we'll go back to my talk. This is not where my talk is. I'm sorry. Yes, here. Okay. So this was the hands-on demonstration. And now I will talk about a few of the ingredients inside Aspect. So it's actually a very complicated thing to have an application like this. Even if you're familiar with the mathematics behind it, there are a lot of things that come together. For example, you need efficient and robust time discretization. You need a spatial discretization and also stabilization that is efficient and works well. You need a way to treat the nonlinearities. And also, everything needs to run in parallel. So there's a lot of different areas that come together. I already pointed out the publication, I think, so there's a lot more detail about this in there. That's basically the main focus of that publication. So let's talk a bit about time discretization. Here I went back to the equations, but I went to the incompressible case where there's no density inside this second equation. If you look at this from a mathematical point of view, you basically have only a convection diffusion equation for the temperature, because this is the only equation that depends on time. And this Stokes system here is an algebraic constraint that you have. Basically, the temperature determines velocity and pressure, and this determines back the convective part for temperature. So we're using an implicit time discretization, second order accurate, and right now we're using an impis scheme where you're extrapolating the velocity, you're solving for the temperature, after that you're solving for velocity and pressure, and then you go on to the next time step. This is the default right now. Obviously, we need to do something more complicated later on. But this is already in the works, and it's just a matter of swapping that out, basically. So in theory, if we had a fixed velocity, this approach would be unconditionally stable. We have no CFL condition, no restriction on our time step size, so we could make arbitrary big time steps. In practice, this is sadly not true, because it's well, the stabilization methods, for example, for this convection-dominated temperature, it would create oscillations if we do arbitrary large time steps. And the second thing is that we have some kind of a CFL condition because of the mesh adaptivity. So if you look at the mesh on the right here, this is a plume rising. So imagine we make a large time step where this plume moves up further in this coarse area. Of course, it's not resolved anymore. So then the result would be really bad. The quality would be really bad. So we have kind of a restriction on how big time step we can make so that we stay in the area where the mesh is refined. Then we need to refine the mesh again and then do the computation again. So we have something like CFL of 1. So we can do we can make a time step that is as big as the fastest velocity travels when going over one cell. Okay. The stabilization method we're using is pretty advanced. It's called entropy viscosity. And what it basically boils down is to, well, as all stabilization methods, you add some diffusion to your system. So kappa is the diffusion coefficient that comes from the physics, which is typically really small. And you add diffusion to stabilize the system to avoid oscillations. And the idea here, without going into detail, is you stabilize, you add viscosity locally where two things are true. First thing is you will only add it there where the velocity is really high, so where it's really convection dominated. And the second part is you only add it if the solution is non-smooth in this area. And this is a difference to many other stabilization methods that smooth everywhere where, for example, the velocity, the convection is large. So that would add a lot more convection, a lot more diffusion, which would smear out the solution more. For the Stokes system, we are using a stable discretization of higher order. For example, we use second order tensor product polynomials for the velocity and first order for the pressure. And this stable system, I'm not going to talk about more tomorrow about this. I'm sorry about this. This is from a different talk. And this system is stable if you have a higher order for the velocity than for the pressure. If not, you have to add some additional stabilization, and we don't need that because we can do higher order discretizations. So you end up with some linear system that looks roughly like this, where you have a velocity block, and this is the discretization of the gradient of the pressure, and this is the discretization of the divergence of the velocity. Going a bit into the linear solvers, we're using a flexible GMRS method with right preconditioning. So we precondition with some operator on the right-hand side. And this is a block preconditioner that uses the Schur complement that looks like this. And I'm not going to explain that much more. But what we're using is we need to have inner solvers in the preconditioner. So we need a solver for our velocity block A, where we're using a multigrid. And there we also do some advanced tricks where we swap between V cycles and full iterations inside the iteration. So for the Schur complement, we're using an approximation based on the scaled mass matrix for variable viscosity. And in summary, the solver is pretty complicated. So for the Stokes system, we have an iterative solver, a GMRS for the coupled system. In each iteration, we apply a preconditioner, and in each of those applications, we apply inner solvers for the velocity and for the Schur complement with, again, inner preconditioners. And this scales very well, so it only takes 15 instead of 10 iterations when going from 10 to the 6 to 10 to the 8 unknowns, which is rather good, I think. So with these technical details out of the way, I want to talk a little bit about the mesh and the refinement. So one example would be to compute on a spherical shell. Well, in aspect, we can use whatever geometry you want. It's not a special case to compute on the shell. You can put in whatever geometry you want. We use curved elements on the boundary with a higher order mapping so that you can accurately represent the curved surface. And what we do is we do a couple of time steps in the order of 5 to 10. You can adjust this in the config files too. And then we refine our mesh. So we check where the solution needs more accuracy and create more cells, and we coarsen the mesh at other places. So here, for example, in this plume again, here this solution is very smooth and we don't need cells. If the plume would move upwards, then we need to refine the cells up here. And the simplest case is to look at the gradient jumps in the temperature at the solution and see where the gradient jumps are large. This is where the plume boundaries are, and there we need to refine. Okay, now I want to quickly talk about the polarization inside DO2 that we are using. I don't need to introduce DO2 because Wolfgang did this last time. So what we're doing, what we want is we want to use finite elements with adaptive mesh refinement, otherwise we couldn't use it. We want fast rebalancing of the workload. For that, we're using space-filling curves. So the mesh is always distributed equally, and so all computer nodes in the parallel computation have the same number of unknowns and the same amount of work to do. And everything is fully distributed, so there's no limit that is there because the mesh needs to be stored on every node or something like that. So we can go to 10,000 and more cores, and we have done computations with more than 1 billion of unknowns, which is enough for aspect in our case. And at the same time, we are staying flexible, so we allow higher order discretizations, coupled equations with multiphysics, and so on and so on. And that is detailed in this paper in case you're interested how that works. So just to give you an example, this is a computation run of strong scaling. So I have a fixed problem of 300 million unknowns, which is quite big, but it's not a Mantle convection. It's a simpler Poisson problem. And I run on up to 16,000 cores, and I look at the wall time. And what I do is from here to here, I double the number of processors. So the best I can hope for is that I need half the time if the problem stays the same. And this is this dotted line here, is the perfect linear scaling. You see that most parts of the library scale perfectly well. going to a very large number of processors. We can also do this for the Mantle convection, of course. So here's a 3D picture. And this is the computational mesh where this solution is computed on. And the color coding here is on which processor these cells live on. So it's colored, as you can see. So this is 50 million unknowns, which is quite small, especially if we look at the strong scaling again. So now the problem is much smaller. But you can still see linear scaling up to hundreds of processor cores, which I think is a good indicator of the possibilities of using aspect for larger computations. The 3D computations are, are still work in progress, I have to say. Finally, before closing, I want to give you an example of one of our contributors, Thomas Gehn, basically, did this. He implemented a new material model. And what he wanted to do was he wanted to have the composition based on the current temperature and pressure. So here you see a diagram, temperature on the x-axis, pressure on the y-axis, and you see the different material phases, how the material changes if you, for example, increase the pressure. And he did this with a chemical simulation offline. He generated this diagram, and he computed all the properties depending on temperature and pressure. And the result was this lookup table. And he read this file in, and he wrote a small one file that he put into Aspect that you can also, it's in Aspect in the current version, so you can try it out. And what happens then is that we can see a nice effect. Namely, you can see a slab lying on the 660 discontinuity. So if you look at the density profile, it has a big jump here due to this chemical material model. And the result is if the slab is, if cold material goes down, it kind of rests on this, because the material below is much denser, so it cannot really penetrate, and so it slowly goes down. And this is an effect that you can see in reality, so that's interesting to see. On the right here, I show the computational mesh. So you see that we resolve the plumes, and we resolve the density layer, and the mesh is very coarse outside this. This is a 2D computation still. He has done 3D computations, but I don't have the pictures yet. So here's the zoom. You can see this plume seems to be penetrating, and this plume is resting as a slab on the discontinuity. And you can also look at, here are some 3D pictures, you can look at the material phases. So remember that depending on temperature and pressure, you can look up a material phase. And so this is now visualized here. And here's some 3D velocity fields of that solution. And you can also compute seismic velocities, because in his material model, he has now the material properties at each location. And now he has generated fake seismic velocity pictures that you can compare to reality, which I think is a really cool thing to do. Okay, and with that, I think I'm done with my program. So I would like to thank you for your attention. I hope you are interested in Aspect. You can check us out online at dl2.org/aspect. And I'm also happy to take any questions, if it works, that is.
Thank you, Timo, for giving such a good seminar. The floor is now open for questions. You can either raise your hand. There's an icon at the top of your screen with a little person that allows you to raise your hand. I can turn on your mic, or you can type something in the chat window. And oh, here's one from Cedric. Timo, are you seeing his question?
Yes, I do. Okay, Cedric is asking, when using Q1 P0 elements, how do I stabilize the pressure? So, as you correctly point out, the Q1 P0 is not a stable element. So you get oscillating solutions. So my first answer would be, well, you wouldn't use that element. The question is, why do you want to use that element? So something you could use, for example, is Q2 P0, which is stable. You can just use that. You just change the parameter to use discontinuous pressure in the examples, and you can run this. If you absolutely want to compute on an element that is not stable, you have to use SOPG, PSPG stabilization. It's not in Aspect because we don't think that's a good idea to do, but if you want to do that, I can tell you what you have to do. Basically, you have to add an additional term to the pressure block to stabilize the pressure. Otherwise, you get checkerboard patterns and oscillations.
While we're waiting for more questions to come in, I wanted to have some reminders. That is, remind you that there is no webinar next month due to AGU, but we hope all of you guys will come by our booth and say hi and see the demos we have running and meet the developers. There'll be times posted on our website. We also welcome you to come to our business meeting on Tuesday night at the Park 55 Hotel. There'll be light refreshments and a cash bar, and come and contribute and learn and meet all of our new staff. I'm not seeing any more questions in the chat or in the participants window. I'll wait a few more minutes and thank Timo once again. Oops, we got 2 people typing.
So thanks, Lorraine. I'm also at AGU, so you can catch me there, and I'm happy to answer questions. And I also uploaded this virtual image to the Aspect homepage under downloads. So if you want to try it out, you just download VirtualBox and you download the image, and you can try out what I did if you're interested. It's a good way to get started, but it's not a good way to run longer computations, of course.
I have somebody typing here. We'll wait to see if there's a question. There is some Aspect videos that Timo has linked to our YouTube page. So if you want to look at some more simulations he's done, go to either our website or our YouTube site and view those. So Katrina has a question.
Yes. Okay. I will read the question. Dan first. He wants to know if I can use something else than Visit. Yes. So I'm actually using ParaView normally, but inside the virtual machine I couldn't get it to work, so I was using Visit. It's the default is standard VTK output, and you can use Visit and ParaView, also in parallel to if you have really big solutions. You can also use HDF5 output that can also be read by ParaView. Other things, there are many others files that are supported inside DL2, so one has to see what works. But VTK output works with Visit and ParaView. Katrina asked, where in Aspect has Jakobs added his lookup table for the phase transition? Is it in the current version? So first, yes, this is based on the Jakobs paper, but the work was done by Thomas Genen, who's in Utrecht. And yes, if you take a look at the current development version, there's a material model called Table, and this is exactly that. So you can try that out if you want. There's a simple table in there that is kind of smooth because Thomas didn't want to release the good table from Jakobs that he couldn't make publicly available yet. But you can also contact Thomas if you have a question about this. I'm happy to send you the context. But yeah, there's a model in there. There's also a model called Steinberger, which is done by René, which is also based on a lookup table, but it's a different model. Maybe even more complicated. I don't understand the model exactly. But you can see that people start using Aspect and they just write their own materials very easily without us helping, really. I hope I answered that question. Good.
Great. I don't see any more activity right now, so I want to thank Timo once again, and see you all at AGU. Wait a second. Dan has the next question here. Timo, you still there?
Okay, yes. So Dan asked what the next phases of development are. Right now we're working on compositional fields. So Juliana and René implemented compositional fields using fields, which is already working, and there are also examples in the cookbook. But there's some work that has to be done there. We have to work on the stabilization and to improve these and to make this more robust. The second thing is tracers are not active yet. So if you want to use active tracers to track compositions, for example, this is something that's on the horizon, being done, being worked on. And yeah, further having more complex physics, higher compressibilities, and making the library more robust. Those are the next goals. I guess that sums it up. Darcy flow is not something we are currently working on, but you can get in contact with me and we can chat.
Okay, I guess I'll thank you once more and sign off and see everybody in San Francisco.
Yeah, thank you. Thank you all.